And you may see some of this on your test. So just to sum up, absorption versus emission. If this is my electron, I have an incoming photon. That energy will be absorbed by the electron. The electron will then move to an excited state. It needs to then emit that. So if I come over here, I see that to move from this excited state back to ground state, it's going to have to emit. So I'm going to have my energy moving away from then the nucleus and out of the atom. Okay, let's talk about the Balmer series. So ultimately, in 1885, we had a scientist, Balmer, who ultimately found, along with Bohr and him both did this, but Balmer knew that hydrogen gave this emission spectrum, but did not know how necessarily it worked. At the time, there was a formula that we call today the Rydberg equation, and that's this formula here. This formula will be given to you on the free response part. It will not be given to you on the multiple choice portion. So this is something, though, that I think that we should know, just because I have seen this as a multiple choice question before. So Balmer sees this hydrogen spectrum, and he wants to know, can I calculate the wavelengths that I should be predicting for each of hydrogen? If I see this, can I calculate it? Can I reproduce this spectrum with math? So this equation is something that he kind of worked on, and it was by total accident that he figured this out. This is the equation that we're still kind of debating right now. This is Rydberg's constant. If this number is wrong, it will totally change the way that we view the universe. So we're hoping that this is correct. But I kind of want to look to, we'll get to another one that looks very similar to this. So maybe let me hold off on that, and we'll come back to this. Let's talk about this. So I have 1 over wavelength. So 1 over wavelength, 1 over lambda, is equal to RH, which is just the Rydberg constant. And Rydberg's constant is 1.09. Let me write it down for us, just so that way we have it in our notes. Oh, that's awesome. Okay, so Rydberg's constant, 1.096776 times 10 to the 7. And it'd be a per meter. So 1.096776 times 10 to the 7 per meters. That's Rydberg's constant. And this number will also be given to you, okay? Okay, so what are N sub F and N sub I? So I have 1 over wavelength is equal to Rydberg's constant, and then N sub F, N is going to stand for that principal energy level, aka what energy level it's in. So NF would be the final energy level, and then N sub I is going to be your initial energy level. So for example, if I'm starting off at ground state, and then I move up 2 energy levels, my N sub I is going to be 1, and my N sub F is going to be 3. So that's really it. So N is going to represent energy levels. This is going to be Rydberg's constant, will never change. And doing this calculation should allow me to calculate what the wavelength will be, so that way I can predict what these emission spectrum or spectra look like for elements, okay? And we find that it works very well. We just don't know how it works, because this equation just kind of happened by accident. So how that happens, I have no idea. It blows my mind still, but this equation is still kind of in debate. So we kind of have already done this, but just because we're going into Bohr's model next, we know that Bohr's model ultimately is that planetary model. So orbits are quantized, meaning that to move an electron from one orbit to another, the electron is going to have to gain a certain amount of energy to move then to that next level. Emission, we know that that just means that the energy of the atom is going to decrease, so electrons are going to move closer to the nucleus. Absorption means I'm going to gain a certain amount of energy, so the energy of that electron or the energy of the atom has to increase, and that means that the electrons are going to move farther away from the nucleus. Ground state is when they're at n equals 1, so that's when they're closest to the nucleus, and an excited state could be any of the other orbitals, any of the other energy levels, okay? So some of the things that Bohr's model talks about. So let's kind of go through Bohr's model here. Bohr makes several assumptions about the atom, and we know that some of the assumptions that he makes are right, but some of the assumptions that he makes are wrong. So he says some of the things that he assumes are that electrons in an atom can only occupy certain orbits, meaning certain energy levels. So that's something that we know that's true. Certain electrons are going to be closer to the nucleus, certain electrons are going to be farther away from the nucleus, but it's going to be dependent on what element or what atom I'm talking about, okay? So I'm okay with this assumption. On assumption number 2, it says electrons in permitted orbits have specific allowed energies. These energies will not be radiated from the atom. So ultimately what he's saying is that we have to assume, or he's assuming, that electrons are going to move in a circular path. They're going to move in a circular orbit around the nucleus. This is a huge problem. If you have electrons that are moving in a circular orbit, just because an electron's speed can maintain the same magnitude in an orbit doesn't mean that it's not changing direction. Meaning that if these electrons moved in a perfectly circular orbit, they would have to start accelerating around the nucleus. If an electron begins to accelerate around the nucleus, an electron would then theoretically fall in towards the nucleus. It would move closer and closer and closer until ultimately an electron and a nucleus were touching. And then at that point, we could have a really big problem there. We wouldn't have atoms, nothing would exist if that were the case. So Bohr's model is limited in the fact that he assumes that he assumes that all the orbits are perfectly circular. There's no way that they can be perfectly circular. There's just no way. So these allowed energies is this circular path. But I think when he says allowed energies, he also means that an electron must absorb a specific amount of energy to move away from the nucleus. And that part I agree with. So number 2 kind of had this dual purpose. Number 3, it says the energy is only absorbed or emitted in such a way as to move an electron from one allowed energy state to another. I totally agree with this as well, and really these 3 things are saying the same thing. I have to have a specific discrete amount of quanta that is absorbed by the electron before I can move that electron to a new energy level, and then it has to emit an energy of that same amount, of that same quanta, so then that way it can go back down to ground state or to a lower energy level. So let's look over here as well. This is an energy diagram based on Bohr's model. I see that at n equals 1, here's ground state. So this is when the electron is closest to the nucleus. This is when my n equals 2, n equals 3, 4, and then infinitely so on. I see a huge gap between here and here. But as I continue to move closer, or as I continue to move farther and farther away from the nucleus, I see that the spacing between these energy levels gets smaller. Why? It gets smaller because I don't need as much energy to move from 3 to 4 because the attraction of the electron at energy level 3 to the nucleus is weak. I don't need as much energy to go to the next energy level because that attraction is already so faded, it's so weak. Versus at n equals 1, the attraction, the electron wants to be there by the nucleus, so I need to absorb tons of energy to move up then to that next energy level. So that's why I see a huge gap here. I see, another fairly larger gap between 2 and 3 compared to 3 and 4, because there's still quite a bit of attraction between an electron here to the nucleus, okay? So that's why we see are spacing different as we move up that energy chart or that energy diagram. This is also kind of giving then limitation to our ladder analogy like we said today in class. When we talk about climbing upstairs, an electron has to gain a certain amount of energy to move up or we have to gain a certain amount of energy or apply a certain amount of energy to move up to the next step. But all of those steps are pretty much even. This is not so much the case. Our ladder and our steps are going to get smaller and smaller and smaller as we move up. Okay, so the energy absorbed or emitted, we can calculate that. I'm using Rydberg's equation here to get to this point. You can derive this equation, I promise you. It's not that hard. So let's look at it. I can calculate how much energy, so the change in energy, or how much energy is being absorbed or